these ions are moving according to those forces, they eventually get to this steady state. And this is a state where they're no longer moving in terms of their net flux. So the movement of sodium going in is balanced out by the movement of potassium going out. And they get to this resting place where they're no longer accumulating on either side. And at that resting place, we stick a voltmeter inside the cell, and that's where we get that negative 70 millivolts, okay? So basically, the resting membrane potential is built upon the ECDF of sodium, which is both going into the cell, and the ECDF of potassium, which is going into and out of the cell, but more out of the cell, and the permeability differences, the fact that we have more potassium channels and less sodium channels, and all of those factors acting together bring us to that resting potential of negative 70 millivolts, okay? All right, I know that was a lot. What questions do we have at this point? What questions do we have at this point? All right, so the resting membrane potential becomes really important because this is what's going on inside of a neuron when it's not being excited. We're going to move on to speak going forward, probably next week, about an action potential. And this is where we actually excite a neuron in order to do work. And so it's really important to understand what's happening in the cell at rest in order to then understand what's happening in a cell when it's excited, okay? All right. So this is kind of the combined sum of everything we talked about today, all of the factors that are at play. We got the sodium-potassium pump. Just to recap those events, the sodium-potassium pump, setting up those concentration gradients, more sodium outside, more potassium inside. We also have the movement of potassium through more channels, which creates this excess negative environment inside the cell. So we got more positive charge leaving, so we got more negative charge left behind. And so that creates our two forces for our two ions. Sodium has a chemical force wanting to go into the cell because of that concentration gradient. It also has an electrical force wanting to go into the cell because the inside of the cell is more negative. So that creates a really strong influx of sodium. And then potassium has a concentration gradient that wants to move out of the cell because of that concentration difference. And then an electrical force that wants to move into the cell, again, because potassium is positively charged and the inside of the cell is a negative environment at this point. And that creates this opposing force where potassium wants to slowly move out of the cell, okay? So we got a strong force for sodium going in and a slow force for potassium going out. And that's how we get to that negative 70 millivolts. Now, as you can see, when you kind of look at this in a big picture way, the resting membrane potential is going to be closer to the equilibrium potential for potassium. Why do we think that is? If we look at the values, we can see that the negative 70 is much closer to negative 94. But in terms of what we spoke about, why do we think that is? What's one factor that we mentioned that could kind of explain this? Excellent. The cell is more permeable to potassium. So at rest, the cell looks a lot like what's happening with potassium movement, okay? Because the cell is more permeable to potassium. But we can also see here that the membrane potential is really far away from sodium's equilibrium potential, right? Sodium's equilibrium potential is really positive. It's positive 60. That membrane potential is going to be negative 70. So in terms of the difference here, this represents the force with which sodium wants to move, okay? So the membrane potential when the ion is at equilibrium, and the difference between that membrane potential and the resting membrane potential is the force or the degree to which that ion is going to want to move to get to equilibrium, okay? And we can see here that sodium really wants to get into the cell because it's really far away from that -70 and it's also positive. So it's going to want to get into the cell. And then potassium is going to kind of slowly want to trickle out of the cell because it's closer to that -70 and then it's negative. So the direction is going to be out of the cell, okay? So this is a really important indicator of the movement of those ions, the value of these equilibrium potentials in reference to the value of the resting membrane potential. All right. Now this is kind of recapping some of that here. The electrochemical driving force is not zero, right? The membrane potential is not at equilibrium for an ion. So if the membrane potential is not at -94, then potassium is going to be on the move. If the membrane potential is not at +60, then sodium is going to be on the move, right? When the membrane potential gets to the equilibrium potential for that ion, then that's where we see zero movement of the ion. And so the net force really acts to move that ion in the direction to favor it becoming at equilibrium. And the strength of that force is the degree to which the equilibrium potential is away from the resting membrane potential. Okay, I hope that makes sense. So the further that ion's equilibrium potential is from the resting membrane potential, the more of a force, the strength or the magnitude with which that ion is going to try to move to get to its equilibrium potential. Okay, any questions here? This is where I kind of start losing students. Any questions at this point? Any questions? Did I lose anyone? Everyone still on the bus? Okay, awesome. All right, so we can look a little bit further at what potassium's equilibrium potential looks like with regard to -70. This is going to be really important as we speak about an action potential. An action potential is going to be moving the ion, the membrane potential, more positive, and then in order to get it more negative, we're really going to rely on the movement of potassium out of the cell, because as we can see, potassium's equilibrium potential is really, really negative, and in order to get the cell back down to rest, potassium is going to have to be moving out of the cell, okay? So it's a smaller difference here. So the membrane potential is only 24 millivolts less negative than that equilibrium potential for potassium. So this -94 is only 24 millivolts less negative than -70. And so that speaks to the degree with which potassium wants to move, right? It doesn't really want to get out the cell as much as sodium wants to get in. It has a slower or more of a trickling effect in terms of its movement. Sodium, on the other hand, has a really big difference in terms of the difference from the resting membrane potential. Okay, if you look at this +60, the membrane potential is 130 millivolts less negative than that equilibrium potential at +60. And so that speaks to the degree or the force with which sodium wants to move. Okay, so although it has less of an opportunity to do so because it has less of a permeability, it has a much stronger force of about 130 millivolts to try to move to get to its equilibrium. And so potassium is going to be really important in the depolarizing phase of an action potential, because that is the ion that can move to bring the membrane potential to a more positive area, which is what we need to fire an action potential. Okay, so sodium's movement is going to be involved in depolarizing the cell to fire an action potential. We're going to talk about that more next week. And potassium's movement is going to be more involved in getting the membrane potential back down to rest, okay, or becoming more negative.